始めたらしいので、今エンジンヤードという、Ruby のホスティングを行っているサンフランシスコの会社で、フルタイムで一番最初ね50% とか言ってたんですけど、いつの間にかフルタイムになってましたね。100% Rubinius のために働いているというハッピーな人ですね。はい、そろそろ準備できるかしら。で、例によって Mac を使っているという。こうしてみるとですね、日本の Ruby 開発者っていうか、日本の Ruby コア開発者のうちの Mac 率の低さは異常ですよね。来い、あれ？あ、来た。
こんにちは。
はい、エヴァン・フェニックスです。写真撮ってますけど、これが日本人だ。はい、日本人見せ物みたいになってますけれども、それでは、ちょっといきなり途中から始まってますが、ちょっと待って、はい、Rubinius の魔法について、エヴァン・フェニックスが語ります。よろしくお願いします。
Okay.
Could you talk a little bit slower?
Sure. If I'm too fast, would someone wave and tell me I'm speaking too fast? Okay. Thank you. Okay, so my name is Evan Phoenix, and I am the main project lead for Rubinius, and I'm going to be kind of talking to you a little bit about what Rubinius is, and then kind of showing you some fun stuff that we have that we like to play with, and we'll answer questions and maybe do some live coding if we want to. Okay. So Engine Yard is my employer, and they very graciously let me basically work on Rubinius full time. It's a dream job. They just kind of let me work at home and play with Rubinius all day. So it's the best job in the world as far as I'm concerned. So Rubinius as a project is a number of actually different pieces all working together. So when we talk about Rubinius, we talk about the whole project as well. So it's an environment for running Ruby code in. But we also have our own virtual machine that we've written. We have our own what we call the kernel, which is all of the built-in functionality of Ruby. So of string, of hash, of array, all of those classes and all of those methods. We have a compatibility layer for running extensions that were written to run on 1.8. So we have the same C functions like RB define method and those sorts of things, so that people can use the same extensions on Rubinius just by recompiling them. And we have a lot of fun. I try and keep the project as fun for people to work on as possible. We have a policy in the project that everybody's okay. It's okay if you're wrong. In fact, I'm wrong more than anyone else in the project probably. And we also have a very loose organization. So whenever someone submits a patch, the first time that patch gets committed, they actually get commit rights, so they become a full-fledged member of the project. They can commit without having to ask anyone after that point. So we try and keep it very fun. But it's also an extremely large topic. I could go in a lot of different directions. I've tried to give a technical talk for Rubinius, and I tried to give it in an hour, and I only got about half done, and that was covering just what the technical areas were. So it's very big. The other thing about this kind of a big project like this is, and we probably won't do it here, we'll probably just wait till the end for questions, but I like to kind of have back and forth with the audience, but I think we'll probably just wait till the end for here. So for nerds in the audience who are interested in what the VM does, this is some, like Koichi-san. We have, these are 3 kind of VM features that we have. So we have an accurate generational garbage collector, which lets us do allocations and making space for objects and freeing up objects very quickly. We have a bytecode-based virtual machine, and the whole system is actually, most of the system is actually written in Ruby. So the system is capable of basically generating all the code for the next version of itself, in itself. So it can basically bootstrap the next version by running itself. That was a big goal that we had. This is my explanation of what Rubinius is in Ruby syntax. It is as though I took a lot of the ideas from Smalltalk, from the way that Smalltalk environments were built. Not all of them, but a lot of ideas. And then we basically included the syntax of Ruby and the behaviors of Ruby into that. And then we also looked at all kinds of research that people do, and we threw that into, just to make things fast and fun. So a big part of Rubinius is that we try and write as much of the system in Ruby as we can. So our VM is not written in Ruby, but so all of our kernel is. So all the methods, like I said, all the methods on, say, string or hash or array are all written in Ruby. So we have two different worlds of Ruby code. We have the kernel land, which there's a directory inside Rubinius called kernel, and all the code that's under there. All that code is pre-compiled into bytecode, and the VM loads it directly without any kind of require or load statements. And it has 3 different phases that it loads this code in. Again, this is just Ruby code that it's loading in. It's already been parsed and it's already been compiled to bytecode, but it is just regular Ruby code that's being loaded in. And the order that it's loaded in is basically kind of encoded in comments in the files. So it's a little weird, but it makes the system very easy to work with. And then what we have what we call Userland, which is all the code that everybody in this room normally writes, which is just regular like IRB, Rails. Those are all sort of Userland code. We like to think of it, we call it these 2 things, like as though we're a real operating system, where you have the kernel doing things that maybe is written in, say, C, and then you have the Userland, which is also written in C, and they interact through certain places. And our interactions aren't as strict as a real operating system, but we it's kind of similar, so we call it the same thing. So because we write so much in Ruby, so much of the system is written in Ruby, what we wanted to do, and this is an idea that we got from Smalltalk, was to make as much of the system as in normal Ruby classes as possible. And the 2 classes that show that a lot are method context and compiled method. And I'll get into what those are in a little while, and maybe we'll do a little quick demo to show you kind of how cool they are. But by having things as first-class objects, you can get a lot of data. So you can run your code and then you can actually go back and ask questions about how it ran, what methods were called when you ran a particular section of code, what the classes of the local variables were. You can go and ask a lot of those questions, which makes things very nice for debuggers and different kinds of things that you might want to learn about the code. And the big thing, which is the last point here, which there's enough information for us to implement our eval completely in Ruby. So we have our implementation of eval uses all the first class objects that we've created, and it's completely written in Ruby that uses our compiler, which I'm going to talk about here in a sec. So the way that we're actually able to do something like eval is that it exists just like you would normally run a file. So the first idea here is the ability to look at your code as data. So we have built in a version of parsetree, which is a program that Ryan Davis wrote that lets you view your code as a very simple representation. So here we are looking at what 1 plus 1 looks like, and it's really just calling the plus method on 1 with an argument, with one argument, which is also 1. And we use this as the very base of how we build the actual compiling of code. So then what we're able to do is the compiler can take in this code and we can get it back out. The compiler will turn that into bytecode, but we can also get it back out. So this is more looking at the actual code that we're running as data. So here what we've done is in Rubinius, I cheat, and when you define a method, the return value for creating a method is a compiled method object that you can go look at to see what that method was that was just added. So here's what we've done is we've assigned meth to the actual method for this test method, and then we've actually asked it to decode the method into its bytecode parts. So we can see here that it takes zero arguments, and then it's going to push 1 on the stack and send plus, and then return. And these meta instructions there are for performance, so that we can do things just to keep things short and fast. So this meta send plus lets us add 2 numbers together without having to call real full methods to keep it fast. So the big part that makes all that possible is that we have our compiler for taking the code in and creating the bytecode all written in Ruby. So that, as we saw 2 slides ago, where we had the S expression for 1 plus 1, that's what we take in as input. And then it transforms that into an internal AST for how the code looks. It adds a lot more data along the way so that we can easily generate bytecode from it. And then it's all set up as a very simple pattern to generate bytecode using this visitor pattern. So there are node classes that implement a method called bytecode. And the bytecode method just calls bytecode in all of its sub pieces, just kind of flowing down the tree and then generating bytecode as it goes back up. And because we've got it all written in Ruby, one really fun thing that we did is we added plugin support to our compiler so that you can actually go write a plugin to change how the compiler works, to either maybe you want to have some custom syntax that does something very special, or you know a way to make something faster. You can just have a plugin. So this is a sample plugin. This is actually one that we have, a very short plugin that we have in the system right now. And I'll let you look at this for a second. So this plugin statement at the top gives our plugin a name. In this case, we're calling it current method. And then all plugin classes just have to define a method called handle, which means whether they're handed some work to do, and they can say whether or not they actually want to perform it, and they are expected to perform the work here. So what we've done is the first thing that you do in a handle method is you find out whether or not you're supposed to be running at all. So every plugin gets a part of the AST, so basically gets a class or an instance, and can determine what it wants to do with it. So in this case, we know that the only thing we want to be looking at is vcall nodes, and a vcall node is basically a call that has no receiver and no arguments. So it's just one class or something really short that doesn't have any arguments or any receiver. So we know that if it's not that, we return false to say, no, we don't handle this one. Otherwise, we look and see if the method name that we're doing is __ method __. That's how I like to say capitals. Otherwise, it's very confusing. And then all we do, if we know that that's the case, we use this local variable, this argument g, to generate the bytecode. And all we have to do is call methods on g to actually generate bytecode for this sequence. So here what we've done is we push context, and we send the method called method with 0 arguments to it. And then we return true to tell the upper system that, oh, we've handled this thing, you don't need to do anything for it. Otherwise, we return false. So what that does, in the end, is it takes this code and it turns it into this, the bottom. So that now, while you're coding, you can say __ method __, and you'll get a compiled method object back that is just the result of running this code. So it works sort of like macros do. You're able to look at code that's running and manipulate it, and then stick it back out. So here's just a quick example of what it would look like. So we are able to, blah can know its own name, for instance, which is something that currently Ruby doesn't really give you. I think in 1.9 has that ability now, but before you wouldn't even know, you sometimes don't know who you are. You know what the method was maybe added as, but you don't know what it was called as. So another class that we have as a first class thing is this block environment. And it encapsulates all the data about how a block works, so that it's sort of the closure plus the data that needs to be run when the block is activated. So here's a quick example of what that looks like. So again, I've cheated, and block given, rather than just returning true or false, actually, I believe it's true or nil. In Rubinius, it returns the block environment or nil. And that works because everybody just uses block given as a conditional anyway. So we've stolen the return value here. And so what we do is we call blah and we pass in a block. The code for that block is to output hello. And we've saved the block environment into a global. Okay. So what we've done here, then we've gone back and we're looking at that block environment that we created earlier. Just by sending blah a block, you create a block environment sort of by default. It's hidden, you don't see it there, but it creates it for you and it hands it into the method. So here what we've done is we've decoded it just like we did before with 1+1, where we can see now what the actual code for that would be doing. In this case, it's a block, so it's always going to have some arguments on the top of the stack. So it's going to pop it off, it's going to push hello, duplicate it, and then it's going to be sending puts to self. So we see it pushes self, and then it's going to send stack, and we have this send side object, which I'll talk about in a sec. And you can see the name is puts, and then it's going to do a soft return, which is just a normal return. And we can also do things like looking at where the actual block was created in. So you can look at home, which gives you this method context object, like I mentioned earlier, to find out where things were when this block was created. And you can even go further, you can find out who self was when the block was created. So you can really dig in, you can find out all kinds of interesting information about your code. So we saw send site in there. So what is a send site? It's an object that lives everywhere that you would be calling a method on an object. So if you write a method that contains 5, typically dots, 5 places that you're going to call methods, that's going to represent 5 send sites. And those are allocated with the method. They're not allocated every single time you call the method. So they live on through every time you call it. And that lets us do things like caching information so that we can make method lookup faster. So typically when you call a method, and typically the second and third time that you call a method, the class of the locals is the same. People typically use the code in one way. They don't use duck typing most of the time. So this lets us speed up dispatch so that we can basically be faster. And here's us, then again, we can easily just look at a send site object. So we've used the same pattern we did before. We've pulled out the compiled method object. And then there's a method on compiled method called literals, which is where all the actual sort of like statically allocated objects live. Strings and other compiled methods and send sites all live inside literals. And so we know that the send site in this case is, I didn't show this, but I looked up where the send site was. I knew it was in 0, so I've pulled it out. And then we can ask it things. So we can print it out, and we see that its name is left. Well, actually, this is a good question. If someone could tell me, what do you guys call this method? I call this left chevron. I don't know what other people call it, but anyway, we can talk about that later. So then what we've done is we've called the method a couple of times. We call it with 1, we get 2 back, we call it with 2, we get 4 based on the code. But we can also then look at that send site. So we can see, oh, it was hit once, we can see it was hit twice, so you can go and you can look at actually what was going on as you call it. And we can do more. We can say, all right, what was the receiver in the last time it was called? What was the receiver? Oh, it was a fixed num object. And who is the owner of this send site? We can see that it's this method called blah that we created in it. And we can also do things like ask a send site for its selector object. A selector object is able to, you can ask a selector object, say, tell me every place in all the code that you have that the method 2s is called. And it can tell you exactly where that is. And you can go and you can find out, say, this is very good for trying to discover what your code does. If you can't say that you have a method and you don't know who calls it, you can easily go and ask the selector, hey, I need to find out everybody who calls this method. And that's just, you ask selector for all of its sites, and then you ask all the sites for all their methods, and instantly you have the data that you want. So next, we're moving on past the compiler a little bit here. So now we have what I talked about earlier, which are these extensions. And what we decided to do when we were first working on Rubinius was that we wanted to be able to let people use all the C extensions that they had already written to run under 1.8 on Rubinius, because that lets people use Rubinius much easier. So things like hprocot or any of the C extensions that people use a lot now, especially since Rails by default, people use 10 to 15 C extensions without necessarily even knowing it. So it was important for us to do that. We didn't want to have to rewrite all those. So we wrote this layer that is still being worked on. It's not complete. And our hope is that we'll allow most extensions to work with just a simple recompile. So that's all you need to do, and now your extension will run underneath Rubinius. So that's a big goal for us. And we right now we can do. I have some volunteers who have been working very diligently on this subtent code, and they've been able to get things. I think we're very close to getting apricot running. We may go back and use SICK, which is the YAML library that Why the Lucky Stiff wrote. So we're getting very close to being able to run very large C extensions. So there's a trade-off, though. And the trade-off is that extensions are seen sort of as second class in Rubinius. In 1.8, extensions use the same API that the internals use, and that makes them very fast. But in Rubinius, in order to actually be able to implement it at all, we had to kind of make them use a separate library. So they have some problems in that they're a little bit slower, but they're accurate and they work. And that's that's what we wanted to make sure that they actually worked. So this is kind of talking again what Koichi-san talked about earlier, which is the multi-VM or MVM functionality. We added it to Rubinius a while, I guess probably 4 or 5 months ago, just kind of for fun. As you can see, we do almost everything in Rubinius just for fun anyway. So we just thought this would be a fun little hack to work on a weekend. So we added this in. It's experimental. It still has some problems, but it is very functional. And I'll show you. I think I have. Yeah. So I have some slides to show you a little bit what the API looks like. It's actually pretty fun. It lets you break up your work into different chunks that can run kind of independently, that just need to communicate small pieces of data back about, say, result sets or that kind of thing. You could do this if you really felt like calculating out, say, digits of pi. You could break it into sub pieces and have each VM calculate a separate piece of pi. Pieces of pi, that sounds good. So this is what the API looks like. You have this spawn method that takes an array that is basically as though you were calling Rubinius on the command line. So you could pass in -v to get the version. You could do any of the normal things you do on the command line here. In this case, we really just want to have it run one little section of code, so we've used -e. And standard in and standard out are all hooked up via pipes so that you can actually start a VM and then you can read back what the VM did just as strings if the other VM uses just like print and read. In this case, we can see that we've read back in that the other VM said hello. So that's not very interesting. So let's look at one that's a little more interesting. So here we're going to use the communication API that's built into it. So this is our first file. This is going to be the client. And so we can see that what it's going to do is for every message it's going to get, it's going to say, okay, well, if the message is exit, print out goodbye and exit. Otherwise, just print out what message you got. And so here, what we can do is we can just run that file in another VM. And we can see here, again, the left chevron method lets us send a message to the other VM. So in this case, we've sent it a message that's the messages are just normal objects. They can be whatever you want. Well, they can't be whatever you want. They have to be simple data structures, like arrays or hashes, symbols, strings, numbers, that kind of thing. Just the kind of the bare bones, easy objects. So what we've done is we've sent it a message saying hello Japan, and then we look at what standard out did, and we see, oh, it printed out the message that we sent it. Great. Then we send it exit, and we look at standard out again, and we say that it's printed out goodbye, and then we can join it just like you could join a thread, and we see that the other one has exited, and now we can go on. It's been cleaned up. So threads. So Rubinius has threading in the same way that 1.8 does. We expose our threading actual library, again, as sort of first-class objects, so that we have a task object that represents a stack of actual running. So you can have, as you have multiple threads, you have one task per thread, so that's how they run, that's how they're set up. We do preemption in the same way that 1.8 does, just with a simple timer, so that we're able to interrupt threads and switch dynamically. When a thread wants to perform some actions that would block the thread, so like reading I/O or that kind of thing, we have an API to talk to our built-in scheduler to do that. And then what we do is we built these channel objects that let us communicate very simply between threads. And the scheduler uses these channel objects. So they're very simple. They're our most basic thread communication layer. And they're very simple, and which also makes them very fast. So here's a little quick example of using a channel. So we create a new one, and then we create a new thread, and we call receive on it in the new thread. And what's going to happen is that this other thread is actually going to block because the channel is empty. So receive is actually going to suspend that thread and switch to a different one. So it's going to switch back to our main thread. So we do this th.run. What that's actually going to do is we're forcing the thread to run, but we can actually see that we haven't run yet. And then when we actually put something in the channel, and then we can ask it again, did you run? We see yes. So that the channels let us basically send and receive values between threads. And when you receive and the channel is empty, then the current thread goes to sleep. And this is a really short example of how we use how we use channels to then let threads interact with the outside world. So for instance, for time, how to actually, we had to figure out how do you implement sleep? You need to know how much actual wall clock time, how much real world time has gone by. So what we are able to do is we have this schedule object, and we just tell it a simple command that we want it to send on the channel in so many seconds. So in this case, C is our channel, and F is how much time we want to wait, which is a float. And T is what to send on the channel. It's a tag, so that we can distinguish it. So we can print now, then we can say, receive, and that will actually block then for the 5 seconds, and then print out the tag that we passed in earlier. And then we can say again, what time is it? We see that 5 seconds have gone by. So the VM operates on these channels and can let things, it lets you interact with the outside world. Again, we use it for I/O as well, so that you can read for reading and writing of I/O, which is communicating with the outside world. Again, signals as well. And then waiting on other child processes. So if you want to execute another process, you need something to be notified when that other child process is exited. That all uses channels. So there's lots to demo. It's a very big topic. Why don't we do a quick demo right now, actually, though, just for fun. So let's see. we'll do this in TextMate. Why not? Perfect. Okay, how does that look? Everybody can read that? And we'll make this
なんかデモしてくれるそうなので準備中です。
So let's go into here. So the Rubinius command that you run to run Rubinius is called RBX. And the reason for that is Rubinius is too long to type as a Unix command all the time. So I had to find something very short. So RBX is what we decided on.
Rubinius はコマンド名としてあまりにも長いので、普段は RBX というふうなコマンドにしています。
So we were just talking about binding of caller. So let's implement binding of caller now. What do you guys think?
JRuby の人たちがバインディングオブコーラの話をしてたので、じゃあバインディングオブコーラ作ってみましょう。
So just to be sure I'm not cheating, let's make sure it's not there.
反則はしてません。
Oh, okay.
ほら、ないでし
Not
ょ。
there. Let's go write it. So the other thing about Rubinius is that if you just run the command, you're connected to a terminal, it runs IRB for you. So it's sort of got IRB built into it.
RBX をそのまま立ち上げると自動的に IRB が起動するようになってます。
So we know that we're going to be in class binding. Ooh, let's put some syntax on. And we know that we want of caller, right? So this is the climactic part. And we're done. That was all. So let's go test it now. We'll write our test at the bottom here, since that makes it simple.
まず foo というメソッドを定義して、レバーというメソッドの中でバインディングオブコーラを実行すると、foo のバインディングが得られるはずなので、そのバインディングの下で、A が求める表示するようにイバルすると出るはず。やってみよう。
So that seems about right. I think we get the binding of who called bar, and then we can see what the local variables were inside that. Let's try it. I don't know if it's going to work. Hey, look at that.
ほら出た。
So this is just a very
質問がある
short.
人は移動し始めてください。
This is just, again, we did this basically in one line. And the whole reason we were able to is because we have these method context objects, and we can inspect them, and we can pull data out of them. So I think I can't talk that as a demo. So why don't we have questions?
はい。エヴァン・フェニックスによる、ルビニウスの魔法という発表でした。彼に拍手を。で、質問のある人はマイクの周りにはいないみたいですけれども、いない？本当にいない？あ、いた。
はい。
小市さん？
ルビカン、数年前のルビカンファレンスで聞いたんですけれども、パフォーマンスどうですかね？How about performance on the Rubinius?
How's the performance? It's getting better.
良くなってきてます。
Because we have so much Ruby code, we have to make it very fast in order to make the whole system very fast. For very small benchmarks, we're a lot faster than 1.8, but that still, we're not fast enough for the whole system to be as fast as 1.8 yet. So we're doing a lot of work to that.
We know that we can realize binding of color such すみません、日本語でやらせてください。バインディングオブコーラーを作る仕組みとかっていうのは実装できるということは分かるんですけれども、さっきチャールズが言ってたように、性能のことを考えるとなかなか外に出せないっていうのがあると思うんですね、コンテキスト情報って。なので、その辺どうですかね。
So we can implement the binding of cola, of course, but it hinders performance. So the Rubinius flexibility might hinder the future performance. How do you think about that?
Yeah, so that's absolutely true. One great thing about building this off Smalltalk is that these Smalltalk programmers figured out how to make it fast in the late 80s. So I get to read their papers and figure out how to make it fast. So for instance, the method context objects, they don't actually exist unless you ask for them. They exist in kind of a ghost state until you actually ask, I want the method context object. And then it can go out and create one for you and give it back. So that keeps it fairly fast.
Thank you.
笹田が分かったみたいですけれども、80年代のスモールトークの実装から言うと、いろいろできることはあるはずで、例えばこの場合だとメソッドコンテキストは呼ばれる前まではレイジに作っていて、呼ばれた時に初めてメソッドコンテキストを作っていますというふうなこんな答えでした。だからスモールトークって結構頑張ってるから、我々もいい線いくんじゃないかなというのが彼の答えです。はい、次の質問は、はい、どうぞ。
Hey, so it's really one thing that's really cool because of so much written in Ruby is that you can, at a high level, have an API for modifying things that are usually very low level. But it seems like one thing where you still have to do very low level work is modifying the parser. So do you have any ideas for high level APIs to be able to modify the parser to, say, for example, at a high level, implement something like keyword arguments?
Sure.
ごめん。
Yes.
質問がよかったので、Rubinius と多くの部分は Ruby で実装されているので、高いレベルで Ruby の、振る舞いを変えると、下のレベルの挙動も変わってしまうんじゃないかですかというような質問です。
So, parser. Right now, we use a parser that is the original parser from 1.8.2 that I pulled out from 1.8.2. What we want to do eventually is have a parser that's all written actually in Ruby for parsing Ruby. We're just not there yet. Ryan Davis has a Ruby parser written in Ruby that he's working on getting to a state that we can start to use it at, but it's just not there yet.
ごめん。こっちに頼って。聞いてなかった。
Yeah. So eventually, yes, we want to have the parser exposed to let you change the parser if you really want to. Although you have to run them by mats at that point.
個人的にはあんまりそのパーサーをいじったり言語を変えたりするのは好きじゃないんですけれども。Yeah, personally, I don't like to tweak the language like a macros or something like that. はい。じゃあ次の質問。
発表の中でコードアズデータとか、シンボリックエクスプレッションをインプットとするっていう話がありましたけど、今松本さんが言われたようなことですけど、マクロみたい、リスプのマクロみたいなものを実装することができるんですか？
So it is possible to implement something like that, the Lisp's macro on Rubinius?
Yes.
できます。
はい。The compiler, macros would be in the compiler, and the compiler is all written in Ruby. We could go in and figure out where in the compiler we want to be executing, look for macros, and then run them. So we could easily do that. The current plugin system is very much like macros already. So we could have something that is able to look at an expression and then substitute in just with macros. Yes.
Ruby パーサーは Ruby で書かれてますし、それ今でも変更可能なようにプラグインシステムで作られているので、書き換えればプラグインでマクロのようなものを実装することができるということです。
いいですか。最終的に目標としていることはどういうことなのかっていうのをお伺いしたいんですが、今は見た目はRuby っぽい形になっていて、内部の構造がスモールトークになってますけど、最終的にはその見た目もスモールトークっていうか、なんか GUI でオブジェクトのインスペクターが開いて中身を見れたりいじれたりするようなところを目指していらっしゃるのかっていうのをお伺いしたいです。
What is your final target? I mean currently we have the Ruby syntax with the small talk inside, but is your goal is about the implementing something like the real small talk, like browsers and
I hope to make an environment that someone else could.
私はその環境を提供するので、他の誰かがそれを実装することができるかもしれません。
We have talked about like having an image, like Smalltalk does, and the VM itself actually doesn't know anything about like the Ruby syntax. It just knows the bytecode. So we could right now, if we wanted, go write a Smalltalk that outputs Rubinius bytecode, all written in Ruby, to run it and make it look like Smalltalk if we wanted. So yes, I probably won't do it, but someone should.
バーチャルマシンはその Ruby のシンタックスについて何も知らないので、そのスモールトークから、Rubinius のバイトコードで変換するようなパーザーを書けば、当然スモールトークというプログラムが動くことになります。で、それからそのスモールトークのイメージベースの実装についても、話し合ったことはあります。で、私自身はやらないけど、そういうようなものを使ってそのスモールトークのようなものを作ることは可能だと思います。でもやらない。私はやらない。
ありがとうございます。
はい、次。はい、お願いします。違うの
We'll talk later.
そこにいただけ。はい。あとですね、Ruby 実装者がこんなに集まる機会はそんなたくさんないのでですね、Ruby 実装一般に関して、チャールズでも、もちろんエヴァンにもですね、笹田さんにもですね、質問が、ローレントもいるので、Ruby のローレント・サンソネッティもいるので、その辺について質問がある人は、どうぞ。
いいですか。
はい、どうぞ。
せっかくなんでぜひ Ruby のその実装者の方にはですね、共通のベンチマークっていうのを作っていただいて、そのベンチマークで競争していただけると嬉しいなと思うんですけど、そういうのは可能性としてはあるんですかね。
それ僕から答えた方がいいですね。はい、実はそのアントニオ名前忘れちゃった。Ruby This Week in Ruby かというブログを書いている、名前忘れちゃった彼がですね、Ruby の共通のベンチマークを作ろうっていう話を、つい先週ぐらいに始めてですね、GitHub にコードを集めてます。で、例えばティム・ブレイが自分の RX っていうプログラムをですね、サブミットしたりとかしているので、そのうちいろいろなプログラムが集まってきて、標準ベンチマークになっていくんじゃないかなという気がしています。で、今 Ruby にあるベンチマークはやる分に偏った結構かなり偏ったベンチマークなので、そういうのじゃなくてもうちょっとリアルアプリケーションに近いようなベンチマークを今作ろうという話が出ています。で、皆さんの中にもですね、このプログラムはですね、標準ベンチマークに入れたいというものがあればですね、確かインフォ Q の最新にエントリーが出てるはずなんで、その辺からググったりなんかして見つけてですね、 まあ、GitHub なんでガンガンこう勝手にこうサブミットするので構わないと思うので、参加してみていただけるといいんじゃないかなというふうに思います。He was asking about the standard benchmark for Ruby. So
Yes, we've started one now that's being worked on. So I think we're getting there.
In the
Yeah.
GitHub. Yes. 田中さんいた。はい。
それぞれの実装で、GC がどのぐらいの負荷になっているか分かりますかね。
Do you have any idea about the garbage collection the shares in the affected performance?
Some I don't have real hard numbers.
正確な数字は分からないけども、まあそんなに大したことはないかなというふうにエヴァンは言ってます。
But I know that the generational part does definitely make it faster. When I originally did the work on it, I wrote a lot of benchmarks to do that, and I'm not sure where they are now, but it was significantly faster.
最初に GC 作った時には、それなりのベンチマークを作っていろいろ試したり早くしたりとかしてました。で、それが、Rubinius で、1.8 についてはあまり GC が問題になったことはないですね。なぜかというと全体に遅いので。で、2.9 についてはですね、周りが速くなったおかげで GC が相対的に目立ってきてですね、ちょっとドキドキしてるんですけども、東大とか電通大とかでですね、Ruby の GC についてのプロジェクトが始まってますし、あと、明日発表する、中村さん、ごめん、名前言ってなかったんですけど、成さんがですね、GC について非常に興味を持っていろいろやってくださっているので、彼の成果がこう 1.9 に取り込まれることもあるんじゃないかなというふうに思います。で、あと JRuby についてはどうなんだろう。Charles, do you have any idea about the how much about GC performance, garbage collector performance?
GC. Well, we can measure it pretty easily. The JVM supports logging GC operations and show exactly how much time, how much memory was collected. And it's not much on the JVM, but it also runs in a separate thread, parallel. But we have seen that reducing the number of objects we create does help performance on like fib benchmarks, not so much on normal applications.
JVM はロギングによってGC のパフォーマンスを測定することは難しくないですし、JVM はパラレルのスレッドを使ってガーベージコレクションしたりとかしているので非常に優秀で GC が問題になったことはあまりないです。ただ、実行中に生成するオブジェクトの数を減らすことによって、パフォーマンスを向上させることができたことはありますだそうです。はい、他に質問がありますか。ちょっと時間オーバーしてるのね。はい、どうぞ。
最近のでかいメモリのところで GC 動かすとパフォーマンスに影響が出るっていうような話を聞いたことはあるんですけど、それぞれの実装でギガオーダーのメモリ積んでる時にどれくらいインパクトがあるのかなっていうのがちょっと知りたいなと思ったんですけど。
一般論として言うと、そのメモリ積んでるメモリの量が多いかどうかは GC にはあまり関係ないですね。で、たくさんのオブジェクトを作っちゃうと結構しんどいことはあって、でそういう時には、世代別を実装している、Rubinius とか JVM の方が、有利は有利ですね。で、CRuby はその辺は非常にナイーブなので、たくさんのメモリたくさんのオブジェクトをアロケートしちゃうと GC の割は相対的に大きくなるというふうに思います。
すみません、ちょっと一般論にすみません追加させてもらいたいんですけど、ヒップがメモリサイズがでかくなるとその GC の停止時間が問題になるっていうご質問だと思ったんですね。でよろしいですか。はい、なので例えばサーバーの方でもインクリメンタル GC をつけようとかそういう話をJVM にはやっているということで、JRuby はそれをそのまま使うことができるということになると思います。
そうですという、JVM はこう GC いっぱい切り替えられたりするんで、ホットスポット JVM とか、その辺ずるいよねなんかその JVM の後ろにいるこう何百人かのチームと戦わなくちゃいけない我々の身にもなってくれって感じまあでも頑張ってます。はい。いくつかのアイディアもありますし、それは実装する予定もあります。はい、今後に期待。はい。もう質問したいって人いますか？手を挙げて。いないね。いないね。いる？はい。では午前中のセッションは終わります。発表者の皆さんちょっと一回立ってもらえませんか？プレゼンターズ、could you stand up？ プレゼンターズ、笹田さんとチャールズはちょっと立ってもらえませんか？で、観客の方を向いて。はい。皆さんに拍手を。ありがとうございました。セッション終わるの15分ほど遅かったんですけれども、午後のセッションは時間通り始まるというふうに聞いてますので、1時目標にですね、集まってください。